Thank you very much. I start by responding to the previous session where it was suggested that our achievements, new achievements in technology may eventually have some kind of doomsday effect of us, that we are creating something which will kill us. I am not in this camp. I believe that technology through the history had liberating effects. And in fact, the more we understand, the more free we will be from all kind of influences of that kind of. It won't be possible to manipulate if we really understand how this whole complex system works. And one of the ultimate complex system is right here. It is inside us. It is the most important personal computer we have. I just started by actually showing the real picture. Usually people, when they talk about the brain, they cut the brain from the spinal cord. In fact, Mother Nature didn't solve it this way. The brain and the spinal cord are embedded in the same kind of package. And the whole thing lives in the sea, which reflects the fact that we came from the sea. Because nervous system, to operate properly, requires external environment which has the concentration of sodium, potassium, calcium, and some other. It's essentially a chemical computer. And it requires this external environment. So actually, our brain swims in the sea, which is artificially created inside us. And so we still live in the sea, essentially. And it's a very smart design from the mechanical viewpoint because it cushions the brain. So when we jump, the brain, which is this mass of neurons, very kind of soft and not strong, because it swims in the sea, so it just protected against it. Also, there is chemical barriers. So when you drink, for example, it passes several chemical barriers before what you drink comes to this area, protected area, which is just in the blue here. Okay, so you see how smart Mother Nature is. It not only designed this wonderful computer from the elements which extremely difficult to design, because you will see that those neurons are really kind of not very fast and not very efficient from the electronic engineering viewpoint elements. Nevertheless, this slow system, which operates in the 100 millisecond range, it outperforms our best computers. How does it do that? Because it has billions of neurons which operate simultaneously. So much about brain hardware. Later, if I have time, I will go a little deeper and show you what is actually inside the brain. The brain is not what you read. Important to understand that if you get knowledge about the brain from the literature about neural networks and artificial intelligence, you're learning about different brain, not the one which is in your head. Okay. So I'm more concerned in this talk with the functional, cognitive possibilities of the brain. So now when you saw, I gave you just this idea what this system really is, the hardware. And now I will talk about what it does. And the most impressive thing, that it has this remarkable unmatched ability, you can probably read it from the screen, to learn. Learning affects everything. It's not just like, say, learning, machine learning in computer when it is just designed to improve, optimize some relatively narrow performance. Learning is actually forming the brain. It is a major Speaking in engineering terms, it's a major software development process. Okay. So I'm concerned with two, because I don't want to overstretch, so I will be concerned with two questions. First question, how can a programmable computing system achieve universality of type 0? I will explain shortly. That's the highest level of universality for Neumann computers and Turing machines. Using basic computational resources, which you can reasonably postulate in this thing, which I showed you, in this biological thing. And second, how this, once we figure out how this architecture may work, how it actually creates almost all its software in the course of learning. Let me go down to now I move to really high-level abstraction. Let's see the big picture. On the right, there is this computing system which simulates the work of the human brain, and we assume that it is possible, and I'm a strong believer that it is possible. It's just that the system. Okay, and then on the left, there is the sensory motor devices and the world, which means every one of us has this world. And you, to me, you are this external world. To you, I'm this external world. But we all have these computers, which I showed you, sitting in our brains. So one computer is now talking to many other computers. So, and my goal is really to communicate my understanding of how it really operates. So let's divide it into two parts, brain on one side, and these devices and the world on the other side. Then we really cut the brain not just between our sensory devices and the world. We cut it inside. So in this case, there are only signals. There are no red, yellow, green, there is no sounds. There is the same uniform signals coming from the system WD to the right and from the system B to this system. Okay. So my first counterintuitive claim is that let's start with the brain B. Well, I call it brain, but I'm actually talking about computing system. And this system DB can be thought of as a human-like robot. But I divided this robot inside. So computing system on one side, and the robot's devices and the world is just another system. It's a convenient way to divide it. Okay, so let's call this B0, brain 0. That's how my website is called. And B0 is some kind of formal representation of B at the moment 0, at the beginning of learning. I claim that this representation starts with something which can fit on a single floppy disk. It's a kind of shocking, probably, statement, but I have plenty of evidence. In fact, so system which is almost empty, almost no software, and I claim that you can say no special language is needed. You can describe it and say C will be fine. But then what happens? Say 20 years passed, and now the system is, well, much more unfortunately passed for this system, but for some of systems sitting in this room, well, 20 years maybe just passed. So anyway, it doesn't matter. These systems now, I claim, no matter what formal representation, no matter what language, it will be in terabytes, just because it should include the individual experience of the system. Okay, so the question is very clear. If you really believe in what I said, you get something which is on the floppy disk, and this system has this ability to suck knowledge from the outside, and it becomes enormously complex system. And how can it do that? Okay, I first start with these levels of, because before talking about learning, usually when people talk about learning, they don't mention what level of universality you're talking about, because there's learning and learning. For example, if system learns to classify something, it's what would be called combinatorial type of machine. So I need to make sure that you know that these levels of computational power exist. Probably many of you already know that. I actually introduced type 4. This so-called Chomsky classification, type 3, type 2, type 1, and type 0. And there are formal languages which very clearly shows that, say, system of type 3 cannot generate language of type 2, and so on. So there are hierarchy of behaviors, complexity, and hierarchy of computing power. So Chomsky starts with level 3. I introduce additional level, lower than that, combinatorial machines, which has much sense for the learning systems. Okay, so what is that? What are these levels? Why they're so important? Let's go to combinatorial machines. Combinatorial machine is essentially a function. It just maps, it's a programmable, in this case I'm talking about universal combinatorial machines, machines which can be programmed in principle to simulate any function. So what resources do you need to build this machine? It's easy to show. You need programmable memory, read-only, but programmable. And you need some fixed interpretation procedure which will read and interpret what is in this memory. In this case, I used programmable memory which has 2 rows. And to explain you concept of interpretation procedure, okay, let's interpret this table, which is A, B, C, B, B, whatever. Let's interpret this, that input is the input alphabet, inputs, all available inputs. And output alphabet of this specific example is 0, 1. Suppose interpretation procedure does the following. It goes from the left and finds the first match, right? Then if I send A and reads the symbol from the second row and retrieves it, what kind of machine will be? Okay, if, say, I send A, it finds the first A and it will retrieve 0, right? So if I send B, it will retrieve 1. If I send C, it will retrieve 0. Suppose I use different interpretation procedure. I go from the right. Then on C, it will retrieve 1. On A, it will retrieve 1. And on B, it will retrieve 0. What it shows you that though machine is completely determined by what is in this memory, how this memory is interpreted depends on the interpretation procedure. Let's use a more interesting interpretation procedure. Suppose it finds all entries of A, right? And then it finds this set, A0, A1, and then, say, at random retrieves with the probability proportional to how many times this symbol is inserted. In this case, this interpretation procedure would interpret this table as probabilistic machine, which means on A it will respond with equal probability with 0 and 1. On B it will also respond with 0 and 1. So for a while, let us assume that we have this fixed interpretation procedure which does exactly what I explained to you. It just kind of finds all the entries and then retrieves with probability. Probability will be very important in the concept which I described because I claim that brain is essentially probabilistic system. Okay. So this is combinatorial machine. Or 4. In my interpretation, kind of my slightly extended Chomsky classification, it's type 4. It's convenient. What is the example? If you know electronics, programmable logic array is a typical example of that. You have programmable AND array, programmable OR array, and the